Good morning. Yeah, so I'm going to have to sort of compress the course in particular. So the notes are fully up, but the section 11 with the strange title, Desperately Seeking Diagonalization, so which is about generalized eigenspaces, I will not do in the class. And I will not ask you to, I mean, you will not be expected to have read that for the exam. So I'm going to go on to inner product spaces after we finish a little more today. Okay, so in other words, chapter 11 will not be in the portion for the exam, though I really strongly encourage all of you to read it, because if unless you read it, you will have an incomplete understanding of linear maps. Okay, but we have only a few more classes left, so I do want to talk about inner product spaces. Okay, so yeah, was there a question? No. Okay, so let us stick with the examples, which is chapter 10, and that is a really important chapter. So I expect you to read that carefully. There will be questions which will be based on the assumption that you have read this chapter carefully. Okay, so so now I've come to part 7, which is nilpotent linear maps. So let V be a K vector space, finite dimensional always, n dimensional. K is R or C, and in fact it can be anything. It's really doesn't matter. Let n hat P to V be hello. Somebody is listening to something and unmuted. A linear map. We say that n hat is nilpotent. So this is an important definition, and this is an important class of maps. If n hat raised to L, which by definition is n composed with n hat composed with n hat L times equal to 0 for some L bigger than or equal to 1. Okay, so now we are going to study nilpotent maps in some detail, and they are a key to everything, including the generalized eigenspace decomposition, so it's really important to understand these well. Okay, so now first of all, what are the possible eigenvalues of a nilpotent map? Well, suppose V0 is a non-zero vector and NV0 is lambda times V0. Okay, so let lambda 0 be an eigenvalue, and so then there is a non-zero vector V0, so that n hat V0 is lambda times V0. So now you just keep applying n hat on this equation on both sides of the equation, L minus 1 times. So then you will get 0 equals lambda 0 to the L V0. This implies that lambda 0 to the L is 0, since B0 is non-zero. This implies that lambda 0 is 0. So the only eigenvalues of an nilpotent linear map are 0. Now, what about roots of the characteristic polynomial of such a nilpotent n hat? Okay, so what do you think? So if K is C, then lambda is a root of P n hat if and only if lambda is an eigenvalue. So we see that the only roots that all roots of P n hat, so okay, the only root is 0. So P n hat T is in fact T to the N. Now, if K is equal to R, we are a bit stuck, because we know that if you have a if I take the characteristic polynomial of a linear map on a real vector space, its real roots correspond to eigenvalues, but in addition there could be complex roots which are not real, in the sense with a non-zero imaginary part, and they don't correspond to an actual eigenvalue with an eigenvector. So the above argument will not work. So, but then we can do the following trick. We choose a basis for V, then consider the corresponding matrix N, then consider the linear map n hat prime from Rn to Rn no, not from Rn to Rn. Cn to Cn given by the matrix N. Clearly, n hat prime n corresponds to n multiplied by n L times. So this should be L. So n hat prime to the L is 0, implies that P n hat prime T is T raised to n, and this implies that P n hat T is T raised to n. So, so this is, I went over this argument quickly because it's a bit tricky. It's not difficult, but it's tricky. But the bottom line is that whether the field is K is R or C, if I have a nilpotent linear map, its characteristic polynomial is actually T raised to n, where n is the dimension of the vector space. Okay, so let me slow down and make sure that you understand. So this, so when I want to say something about a linear map on a real vector space to itself, there is no, at least with the techniques that we have with us, there is no natural way to associate a linear map from a complex vector space to this. Okay, unless I choose a basis, consider the matrix, and once I have a matrix, that matrix can be thought of equally well as acting on real column vectors as complex column vectors, and then I can think of that. I can consider the corresponding map of complex vector spaces, conclude something about its eigenvalues and characteristic polynomial, and then go back to my original linear map on the real vector space. So this is a technique that that we have to use because, let me repeat, with the tools that we have with us, there is no natural way to associate to a linear map from a real vector space to itself, a linear map from a complex vector space to itself. Now, why would one want to do that? Because for complex linear maps on complex vector spaces, there is a nice bijection between eigenvalues and roots of the characteristic polynomial. Okay, so that was a long argument, but let me just keep this here and give you time to think about the argument and ask me questions about it. Gautam Vishwanathan, are you there?
Yes, sir.
Yeah. So do you see the point of the contortions that I'm doing? I'm doing something slightly contorted, but it is not a very difficult contortion, and you should be able to follow what I'm doing. So
yes, sir.
Yeah. So
yeah, I think I do follow. Yeah.
Yeah, Srimati.
So I'm thinking.
Okay. Okay. Siddhant.
Yes, sir, I think I follow, but I'm just going through it again.
Okay, okay, okay. Avinash Rathore, are you there?
Yes, sir.
So I'm giving you time to really think about this, because this is, as I said, it's a complicated argument. So are you thinking? Are you getting it? Are you stuck?
So thinking.
Yeah. So see so I think one thing everybody has.
Excuse me, sir.
Yeah, yeah. Who is this? Shakti?
Yes, sir.
Yeah, tell me.
So could you please go over it again, like this thing?
Yeah. So first of all, I have, at the time that I introduced the characteristic polynomial, I made this, I emphasized this point quite a lot, but I'm not sure that all of you paid attention and you have really, internalized this point. And I don't blame you, because even, it takes a while for this point to sink in. Eigenvalue, a scalar is an eigenvalue if there is a non-zero eigenvector. It has, so the notion of an eigenvalue has nothing to do with any polynomial or its roots. On the other hand, there is associated to every linear map, there is a polynomial of degree n, where n is the dimension of the vector space, such that any eigenvalue is a root of this polynomial. But the converse is not true unless you are dealing with an algebraically closed field. So in other words, in our case, because we are only looking at either R or C, in the case of linear maps from a complex vector space to itself, there is no difference between an eigenvalue and a root of the characteristic polynomial. But in the case when the field is not algebraically closed, that in our case that means R, only the real roots of the characteristic polynomial are eigenvalues. So take the characteristic polynomial, it's a polynomial of degree n with real coefficients. It will have some real roots, and then it will have a bunch of complex roots which will occur in complex conjugate pairs. For example, if I take the polynomial x squared plus 1, it has no real root. The function x squared plus 1 doesn't vanish for any real value of x, but it vanishes when once I go off the real line into the complex plane. Sure, it vanishes at x equal to I and x equal to minus I. So if I have a linear map whose characteristic polynomial is t squared plus 1, then it will have no eigenvalue and no eigenvector if it's a linear map from a two-dimensional. So okay, supposing I give you a linear map from an n-dimensional complex, n-dimensional real vector space to itself, such that the characteristic polynomial is t squared plus 1. First of all, before I go on, what is the dimension of V?
2.
2. Yeah. So it's a linear map from a two-dimensional real vector space to itself. But the polynomial t squared plus 1, the polynomial function t squared plus 1 is everywhere. As long as t is a real number, the value of this of t squared plus 1 will at least be equal to 1. So it cannot vanish anywhere. So there are no roots. So in fact, the corresponding linear map has no eigenvalue. On the other hand, if I have a linear map from a two-dimensional complex vector space to itself with characteristic polynomial t squared plus 1, this characteristic polynomial has two roots, plus I and minus I. And so there should be an eigenvector corresponding to plus I, and there should be an eigenvector corresponding to minus I. Okay, just give me a minute, a few minutes, I'll be back. நீங்க வர வழியில மலை தண்ணி இருக்கா ரோட்ல மலை இருக்கா காரணம் ஓடுதா பால் மட்டும் காய்ச்சி வச்சிருங்க. ஃப்ரிட்ஜ்ல இருக்கு. Yeah, sorry, I'm back. Yeah, so if I take a polynomial on a two-dimensional complex vector space whose characteristic polynomial is t squared plus 1, then it has two roots and there will be two eigenvectors and eigenvalues. Okay, so yeah, so now here so here what am I trying to show? I want to show that supposing I am given a linear, okay, so but before I go to the real case, let's look here. Look at this paragraph first. So the question is, have you, first of all, have you understood the definition of a nilpotent map? Shakti? So that is the starting point of today's discussion.
Yes, sir.
Yeah, so we understand this. Then I asked, what are the possible eigenvalues of a nilpotent map? So supposing lambda 0 is an eigenvalue, that means there is a non-zero vector such that this equation is satisfied. Now you apply n hat L minus 1 times to both sides of this equation. On the left, you get n has raised to L, but that is 0, so that is 0. And on the right, each time I apply n hat to the right-hand side, I will pick up a factor of lambda 0, so I'll get lambda 0 to the L. So I get this equation, and since this is non-zero, this is 0, and if this is 0, lambda 0 is 0. So that is the argument that the only eigenvalues of a nilpotent linear map are 0. So this has nothing to do with whether this is real numbers or V is a real vector space or a complex vector space. This is a general statement. Are you okay so far? Everybody?
Yes, sir.
Okay. Now, but what about the roots of the characteristic polynomial? So, well, then this is where my what I was saying just now comes into play. If k is c, there's no difference between roots of the polynomial, characteristic polynomial, and eigenvalues. They are the same. The set of roots is a set of eigenvalues. So, and since the only eigenvalue is 0, the only root is 0. And if I have a polynomial of degree n whose only root is 0, that has to be of this form. Everybody okay so far? Madhav, CS?
Yes, sir.
No, you don't seem very convinced.
No, I am.
You are
Fine.
convinced, very good. Now, but what happens if k is r? So if k is r, if I'm looking at a linear map from a real vector space to itself, as we saw, there is a difference between roots of the polynomial, roots of the characteristic polynomial and the eigenvalue. So just because the only, so we can only conclude so far that the only real roots of the characteristic polynomial are 0, because the real roots correspond to eigenvalues, and eigenvalues the only eigenvalue is 0. So it could be that there's a nilpotent linear map from even a two-dimensional vector space to itself, okay, which has no real root, but is nonetheless nilpotent. Okay, so now we do this trick. Consider the linear map n hat. Choose a basis for my vector space. Look at the corresponding matrix n with respect to that basis, and now take that matrix to define the linear map from Cn to Cn, and because there is already the notation n hat is taken, call this n hat prime. So that is the first step in the argument. So is everybody okay till this point? Shakti?
Yes, sir.
Okay. But now I take this linear map Cn to Cn and raise it to the Lth power. So let me just make this clear. This is raised to the Lth power. But what does this mean? This means composing n hat prime with itself L times. But that corresponds to the matrix n multiplied L times with itself. But because n hat raised to L for my original real vector space is 0, n raised to L is 0. So this matrix product is 0. Therefore, this is 0. Therefore, this is a nilpotent linear map. Therefore, its characteristic polynomial is t raised to n, from which a little argument, since the characteristic polynomial does, only depends on the matrix, this is t raised to n. So that is the argument. So conclusion.
So what you said earlier was that even if the nilpotent matrix, like if a matrix from real vector space to real vector space, like the linear map from real field to real field is nilpotent, but the polynomial is of form something like t square plus 1. Then how do
no. Then I was not talking about a nilpotent matrix. So in fact, all this argument shows that that a nilpotent matrix, that if the characteristic polynomial is t squared plus 1, it is not nilpotent. No. So you misunderstood me. I was just saying that you could have a linear map from a real vector space to itself, two-dimensional real vector space to itself, with no real roots. I mean, it could have but the nilpotent. So this argument shows that such a linear, if the characteristic polynomial is t squared plus 1, that linear map is not nilpotent.
Oh, thank you, sir. Got it.
Yeah. So conclusion. If n hat is nilpotent, it's t raised to n. Okay, so now in the notes, I have actually given it as an exercise the following, that with respect to a suitable basis, which in the exercise I tell you how to construct the matrix of n. So this is true whether K is R or C. Of the form. Zero, 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 zero here. And in fact, you can even yeah. So it is what is called strictly upper triangular. Okay, so this is an exercise in the notes, and I will ask you to read it. So as I said, yeah, was there a question?
Yes, sir. Like in the above conclusion, it's like can the field be other than R and C?
Yeah, it can be anything.
Yes,
Yeah.
sir.
Yeah. Did you have a doubt?
No, sir. Like that was my doubt. Like
Yeah. It can be anything. Yeah.
So because we had proved it only for like R, so it's like
No, see, in our course we are considering R or C. That is all. Okay, because I didn't want to mess with other fields, and till we came to the characteristic polynomial, it did not matter whether it was R or C. But once we began to study eigenvalues and eigenvectors and characteristic polynomial, it becomes important to distinguish the two cases, which is what I have been doing. But essentially, the difference is between whether the field is algebraically closed or not.
yes, sir. Yes, sir.
Yeah. Yeah, it's a real pity that I'm having to skip chapter 11. I really strongly urge people to read it on their own because it contains many important topics. Okay, so now we come to real vector spaces. Real inner product spaces. This is section 12. So let V be an n-dimensional real vector space. So definition, an inner product on V is a map V cross V to R. And as usual, I'm not going to give this map a name, but I'm going to give it a notation. What it does is it takes two vectors and sends it to a real number, which I will denote like this. Okay, so it's a function from V cross V to R, but I'm not going to give it a name. Okay, but I will give it a notation. So which is one bilinear. That means A1 V1 plus A2 V2 W is A1 V1 W plus A2 V2 W, and a similar equation with plus similar, in which the W is written as a sum of two vectors, two symmetric and three positive definite. I.e., So actually, you don't need to add this. It will follow from other things. Okay. But it's good to note that. So it is a so the standard, the model of this. In fact, this is essentially the only way with respect to a suitable basis. Every thing will be a dot product. Okay. So, but yeah. Okay. So this is modeled on the dot product on Rn V W equal to sigma Vi Wi.
Excuse me.
1 second. Yeah, tell me.
Sir, can you scroll it a little bit up because my network connection was not very good at that time.
Yeah. Okay, sure. You want, yeah. So I'm now, I hurried over nilpotent maps, then skipped chapter 11, and now I'm talking about real inner product spaces. So
Yes, sir. From real inner product spaces, I could not like.
yeah.
manage.
So I'm taking an n-dimensional real vector space, and I define an inner product on V to be a map from V cross V to R. That means it takes pairs of vectors and gives you a real number, and it's bilinear and it's symmetric. And it's positive definite. That's the most important property. So the standard example of inner product. So a real vector space together with an inner product, it's called an inner product space. Okay. And the standard example of an inner product space is Rn itself, where if I take two n-tuples of real numbers, the scalar product is the component-wise product summed. So take the first component of V, take the first component of W, take the product, take the second component of V, take the second component of W, take the product, and add up all these guys. So that is the standard example of a scalar product. It's clearly bilinear, it is symmetric, and it's positive definite because, so for example, positive definiteness. VV is sum over I Vi squared, and this is clearly bigger than 0 because it's a sum of squares of real numbers, and it's 0 if and only if each Vi is 0, which means that it's a 0 vector. Okay. So here is an example of an inner product space, something you are familiar with. We will prove that this is more or less the only example in a sense that I will come to later. Okay.
Hello,
So,
sir.
Yeah.
Sir, I had a quick question on the previous topic. I mean, on the last topic, just one question. That
Okay.
when we are when the field is real, then when we are considering the nilpotent map, there we are considering it to be from Cn to Cn. So there the C to the n is the vector field over the is the vector space over the field C, right?
See, right. Yeah.
Okay.
So take a nilpotent. So see, you realize the basic problem is that, as I said again and again, we don't have a way of associating. So supposing I'm given a linear map from a real vector space to itself, we don't have a way of associating in a sort of natural way a linear map from a complex vector space to itself, because we don't have a natural way of associating a complex vector space to a real vector space, unless if the real vector space is R, then of course it's the associated complex vector space, there is C. And if it's R to the n, I can just take C to the n. And if I'm given an n by n matrix, I can, with entries which are real numbers, I can think of that as real numbers are special cases of complex numbers. So I can think of that n by n matrix as giving a map from Cn to Cn. Okay. But supposing I'm given a linear map from a real vector space to itself, unless I choose a basis, I don't have a matrix. But this doesn't matter in this case, because characteristic polynomial is independent of the choice of basis. So I can go back and forth between basis and the vector space. So that's a trick that we have used. With a little more, so if we had, so the word I'm kind of, yeah. So if we had something else, if I had, yeah, I don't want to go there. Okay, so let's stick with dot products. Can I come back to dot products?
Yes, sir. Yes.
Yeah, inner product. Sorry. Yeah. So supposing I am given an inner product. So given an inner product space V. So that means V plus this. Okay, that's what one means by an inner product space. We define the length of a vector by to be, so this is the length. This is just, I take V, inner product V, that is a positive real number. So I take its positive square root. That is the length of V. Also call it norm. So now, so the length defines a function from, so you have the map V going to mod V, norm V. This is a map from V to where? If I assign to every vector its length, it's a map from the vector space into what set?
Non-negative.
Non-negative real numbers. Okay, because I'm taking the positive square root. Okay, and it satisfies this is 0 unless V is 0. This is the positive definiteness of the inner product that we had seen before. If I take a scalar and multiply V, this is equal to, what should come here?
Mod A.
Mod A. Okay, that's because this is by definition, I take AV and take its square root, which is square root of, by bilinearity, this is A squared V. This is mod A times EV. This is A mod A. And most importantly, it satisfies the triangle inequality V plus W less than or equal to okay, so let's try and prove the triangle inequality. Proof. Um, So here I've used bilinearity and symmetry. Okay, using
So there should be a square over norm W.
Thank you. Thank you. So now one more ingredient. If I take any two vectors, this is less than or equal to and then this will follow. I put all these things together and triangle inequality follows. I'm not going to prove that now.
Should there be a norm on the LHS?
Thank you. Okay, so yeah, I'm now going to spend time on this guy. This is the crucial input. So the triangle inequality is very important. It actually tells you that if I I will be okay now. Let me just say this is the Cauchy inequality, Cauchy-Schwarz inequality. There are in mathematics at least 100 Schwarzes, and they are spelt in almost 100 different ways. So yeah, so the crucial ingredient in proving the triangle inequality is the Cauchy-Schwarz inequality, which I will come to in a minute. But before that, a remark on the triangle inequality. Remark. Define dVW to be norm of V minus W. Then dV V1 V2 is less than or equal to dV1 W V3 plus dV3 V2. So this tells you that this is a distance function. This follows from the triangle inequality. And shows that D is a distance function on V, i.e. defines a metric. Okay, so that's just a remark. So given an inner product space, if you define the distance between two vectors as the length of the difference, that is actually defines a metric on the vector space. So then you can you can define continuity and everything with respect to this metric on that set. Okay, so the triangle inequality is a big deal, and it follows from the Cauchy-Schwarz inequality. So what does the Cauchy-Schwarz inequality say? So let's recall the Cauchy. I'm going to write it down again. So is that if V is a real inner product space, V together with the inner product, then any V W in V, if I take the inner product of V and W, that's a real number. It can be positive or negative, but I take its absolute value that is less than or equal to the product of the norms of V and W. So we can, one second, the angle theta between two vectors to be such that VW is cos theta. Yeah. So there was a question. Yeah. What is the question?
So I didn't get how we define this triangular bracket thing, like VW inside the triangle bracket. Is it the inner product of the vector VW?
You mean you didn't get here?
Yes, sir.
So this is the definition. So an inner product is this data. You take a vector space and you give yourself a map which satisfies these properties. That is the definition of an inner product. Then I said the inner product is modeled on, you are right, the motivation for the definition of the inner product comes from the dot product, which is what I have considered here. If your vector space is Rn, you are familiar with this definition of the inner product on Rn. So this is an example of an inner product. But an inner product is just an abstract package. You take a real vector space and give yourself a bilinear map from V cross V to R, which satisfies with symmetry and positive definiteness. That is the definition of an inner product.
So we are discussing the length of vectors on the basis.
No. So supposing I am given a real vector space, there is no notion of a length. There is no notion of angle. If I'm just given an n-dimensional real vector space, there is no, God has not at the same time given you the notion of a length or an angle. That is additional data. If the vector space is Rn, then there is a natural choice of an inner product, and therefore there's a notion of a length and an angle. But otherwise, there is nothing. On an abstract real vector space, you're not given a length function, you're not given an angle function between two vectors. That is the point. That is an additional datum that you have to give.
Okay, sir. Thank you, sir.
Yeah. Now the point is, suppose, see, the point is, yes, an example of an inner product is on Rn, you take the dot product, which is what you're familiar with. Now, supposing I am given an inner product, I define the length to be the square root of the inner product of V with itself, positive square root, and that it satisfies all these properties. In particular, it satisfies the triangle inequality. Once you have the triangle inequality, you can use the norm, you can use as a distance function between two vectors, and that defines a metric space structure on the real vector space. And the triangle inequality follows from this inequality, which is the famous Cauchy-Schwarz inequality. So I'm just put down the Cauchy-Schwarz inequality, and we are going to talk about its proof. So maybe so for the moment, forget this business about angle. Okay, so let me just remove it. I think it might be just confusing. This is the Cauchy-Schwarz inequality. Just stare at it. So it follows, the Cauchy-Schwarz inequality follows just from the axioms of the inner product.
So can I have some?
Yeah.
So for real numbers, for example, like in the dot product case, obviously the what is it called, the inner product depends on the choice of basis, right?
Sorry?
So I'm saying in the dot product case, in the real spaces,
yeah,
the inner product depends on the choice of basis.
No, but see, the point is in Rn, there is a natural choice of basis, and I define the inner product using that choice of basis. Your question is, are there other inner products possible on Rn? Sure, there are.
Yes.
Yeah, there are other inner products, but on Rn, there is a natural choice of an inner product because Rn comes with a natural basis.
Okay, so for example, for any vector space, I mean,
any vector space, you can choose any basis and declare the inner product to be given by. Yeah,
okay,
you can do that.
and these axioms will still be satisfied.
Sorry.
And these properties will still be satisfied, like.
Well,
I mean,
because you know because the properties that you have to check are 1 to 3, and they are all trivially true, right?
Okay, yeah, thank you.
Yeah.
Sir.
Yeah, but the interesting question is, what are all supposing I am given one inner product, what are all possible? Is there some natural structure on the set of inner products on a real vector space? There is indeed. It is actually, are you familiar with groups and coset spaces? No. Okay, it's actually a coset space. Yeah. So there was another question. Yeah, go ahead.
Yes, sir. To clarify, so do we define the inner product with respect to a basis also, or I didn't fully catch that?
No, an inner product is an inner product is this. Inner product is just a function.
Okay.
Yeah.
Okay, and its value may or may not depend on the choice of basis that we use, or are we even bringing the basis into the picture?
Don't think about the basis yet.
Okay.
An inner product is just some function like this. Okay. Okay, your question is, do inner products exist? You can ask. Okay. Then the conversation that we just had becomes relevant. Choose any basis. Take two vectors. Take the coordinates with respect to that fixed basis. Take the product of the coordinates and take the sum. Check that properties 1 to 3 are satisfied. Therefore, inner products exist.
So could you repeat that one more time? My internet.
Okay. So no. So the question is, do you understand the definition of an inner product on a vector space?
Yes, sir.
Okay. Now, immediately you can ask, does an inner product necessarily exist on an n-dimensional vector space? Because it could be that I made some fancy definition, and there is no, there are no inner products.
Right.
So just to counter that, I say choose any basis for the vector space and define an inner product to be the inner product of V and W is the sum of the products of the coordinates of V and W with respect to the basis.
Okay.
Check that properties 1 to 3 are satisfied.
Right. Okay.
They are trivially satisfied. Therefore, okay. Now, in general, if I choose another basis and do the same thing, these two inner products will have nothing to do with each other.
Okay.
That's what you would say. But nonetheless, I'm saying the set of inner products on a real vector space does have a good structure, which can be explained. Not too difficult. Yeah. But for the moment, let's just assume that a basis, an inner product is given, and let us try to prove the Cauchy-Schwarz inequality.
Okay, sir. Okay, sir.
See, the magic is that the Cauchy-Schwarz inequality only depends on properties 1 to 3 of the inner product.
Right. Okay, sir. Okay.
Yeah. There was another question on the way.
Yeah, so or any space which is metric, like when metric is defined, one can not necessarily have inner product, right?
Sorry.
Like all metric space, are there inner products too? Inner product space too?
No, because the metric space need not be a vector space to start with, no?
Achha, metric space on a vector space, will they have inner product?
Your question is not clear. Say it again.
Okay, if a vector space has a metric defined on it, will
Yes,
it also
yes.
have an inner product?
You mean, does it necessarily come from an inner product?
Yes.
Yeah, so you think about it. So
I was thinking as the sum is defined, so we can define that sine theta, like in terms of angle.
No.
Define.
I mean, you just think about it. This is the answer is no. But I think since you raised the question, you should at least spend 10, 20, 30 minutes thinking about it.
Yeah, I was thinking a bit like.
No, think about it on your own time. Yeah, and then we can discuss this. Your question is supposing I'm given a real vector space and a metric on that. Does it come from an inner product? Is that your question?
Yes.
What is the simplest real vector space you can think of?
Rn.
R to the 100? What is the simplest case of Rn you can think of? R itself?
Yes.
Okay. Now, just think for yourself. I mean, can I put a metric structure on R, namely a distance between 2 points satisfying the inequalities for the metric, so that it is not given by an inner product? Just ask yourself, and then spend some time thinking about the question.
Oh, okay, sir. So I'm like my question was actually, if an inner product, if an metric is defined on a vector space, will it also?
What do you mean by metric?
Product?
What do you mean by a metric?
Distance function.
Distance. Yes, then what is your question? Supposing a distance function is defined on a vector space, then
does it have an inner product? Like all vector spaces aren't inner product space, right? So given that
all vector spaces, what?
All vector spaces aren't inner product space.
No, see, vector space together with an inner product is called an inner product space.
Yeah, like
I just said at the beginning that every vector space, there are lots of inner products, because I choose a basis and take the sum of the products of the coordinate. That's an inner product.
Okay, yeah, for real. Okay, so
yeah. Okay, so I think I think we have a lot to think about. So let me okay, so yeah, so I will revisit these questions in the next lecture. But how do you prove the Cauchy-Schwarz inequality? Proof. Consider the function T maps to So this is a quadratic polynomial in T. Which has at most one real root, since it never takes negative values. Right? Because if I have a quadratic polynomial function, if it has two real roots, it must be like this. And so it will take negative values. So it has at most, so in other words, it has at most one real root, which means 4 VW squared less than or equal to 4 W squared, which is Cauchy-Schwarz inequality. Okay, so this is the argument. So I will give you guys time to look at my notes, and you should really understand this proof well. Okay, this is not difficult. Okay, okay. So now coming back to yeah. So I'm going to stop the recording, and I want to engage with